Okay, and we're back after this word from our sponsor. So, what about the mean? And this says means and variances, and we're going to throw a word in here. Means and variances and standard deviations, because we talk about standard deviation. When we talk about spread, we talk about standard deviation. Variance is the standard deviation squared. The very last step when we did standard deviation, we took, and I'm pointing at you like this, so it's backward. So we took the square root of a variance to get the standard deviation. Most of the time, however, we're going to talk about this as being standard deviation, and that's fine. But we're also going to have to use the word variance here as well. Alright, so the mean of a discrete random variable is its weighted average. Each value of x is weighted by its probability. It's weighted average. You probably at one point should have done a weighted average in Algebra 1 or Algebra 2. Okay? The mean of a random variable is called the expected value of x. So expected value and mean are interchangeable. And this really makes a lot of sense, because if I said to you, okay, let's say that we take a look at the quizzes that you did for chapter 15, and I say, okay, out of 14, the average was 12, and then someone comes into class and is going to take the quiz, and we know nothing about them as a student. We say, well, what value would we expect them to get? Well, we'd expect them to be average. So we would expect them to do the average and get 12. If I was going to say, okay, so here's a distribution of people, and we're talking about their height, and look, it's normally distributed, and I was going to pick someone at random, what would their height be? We would expect their height to be pretty average, because that's what we would base it off of. Well, let's get rid of that. So expected value and mean are the same thing. You're going to have to write some of this out. And the formula here is, as it's really small, is that the mean or expected value of the distribution x is equal to the summation of x sub I, p sub I. Let's write it out. X sub I, p sub I, meaning each value of x times its associated probability. If we were going to talk about, let's wash the board because I need this space here. If we were going to talk about the expected value of our distribution we just did with the sum of the two die, what I would have to do is I'd have to take each value, and each value would be the sum of the two die, so I'd start with 2, because the first sum I would get with 2, and I would multiply that. 2 is the x sub I, x for the first value of 2, multiplied by its associated probability. Its probability was 1 over 36. So I'd have 2 times 1 over 36, plus. Next value would be 3. 3 times its probability, there were 2 out of 36 ways I could get that, plus 4. How many ways could I get 4? There were 3 ways out of 36, plus, dot, 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 add them all. And when I get them, what is that sum going to be? Well, that sum is going to be what that average was 7. As we do this, we'll see how we're going to write this and what we actually have to do in order to get all the points that we want to get for this. Okay, now, what the law of large numbers says in accordance with this, it says, as the number of observations increase, the mean of the observed values, the mean of the sample, approaches the mean of the population. That's really how we defined the law of large numbers before, when we said, if I take a coin and I flip it 5 times, well, let's go with 10. If I flip that coin 10 times, it's fairly likely that I could get 7 out of 10 heads. But as I increase the number of flips, or as I increase the number of observations, that average that I get of heads, or that probability I get of heads, or that response that I get of heads, that mean is going to be closer and closer and closer to the theoretical or the population value of 0.5. And it's because it's going to be harder and harder to get that extreme value. Everything's going to converge to the mean. And there's actually a phrase called regressing to the mean. Things regress to the mean. Okay. Rules for random variables for mean. Okay, if x is a random variable and a and b are fixed numbers, then the mean of a plus bx is equal to a plus b times the mean of x. Wow, that's a whole lot of stuff there. The mean of a plus bx is equal to a plus b times the mean of x. What the heck does that mean? All right, we've done this before. We did this before. We've done this before at least 2 times so far. So let's insert a new page after this and let's talk about this. Say I've got the distribution 1, 2, 3, 4, 5, and I'm going to call this distribution L1. All right, so here's what we're going to do with this. We're going to sit there and say, okay, what's the mean of this distribution? The mean of this distribution, and I'm going to call this the entire thing. This is my population. So when I talk about mean, I'm going to use the population symbol for me, mu. I'm going to say mu sub x is equal to 3. Fine. Okay. So what happens if I take L1 and I add 3 to the entire distribution, meaning everything gets added by 3. So that means instead of 1, 2, 3, 4, 5, I have 4, 5, 6, 7, and 8. Okay? 4, 5, 6, 7, and 8. What is the mean of L1 plus 3? Notice I wrote it like this. What is the mean of L1 plus 3? So the mean of L1 plus 3, which we just saw, 4, 5, 6, 7, 8, is 6. Okay? But what we learned a while ago is that if I take a distribution and I add a value to it, that measure of position, which the mean is, because the mean is right there, it's a measure of position. We said that measure of position is changed by the addition, or that measure of position is changed by the addifier. So what we said before is I could take the mean of L1 and add 3 to it, and the mean of L1 was 3, 3 plus 3 is 6. So the mean is changed by the addifier. What happens if I take L1 and I multiply it by 2? So I say 2 times L1. So what I'm looking for here is I'm looking for the mean of 2 times L1. All right, so if I take this distribution and I multiply it by 2, I get 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. What's the mean going to be? 2, 4, 6, 8, 10. The mean was going to be 6. But what we said before, if I take a distribution and I multiply it by a value, that mean is changed by that multiplier. So, measures of position, the mean, there it is changed by the multiplier. So what we said before is that this would be equal to 2 times the mean of L1. 2 times 3 would be 6. Okay, so what would happen, now I'm going to erase this because I need the space here and I don't want to just insert a new page. What would happen if I took the distribution of L1 and I said, all right, let's take L1 and what we're going to do is we're going to multiply it by 4 and then we're going to add 5 to the distribution. Okay, so I take every value and I multiply it by 4 and then I add 5 to each value. So I want to find the mean of 4 times L1 plus 5. And I'm going to rewrite this so that this is the mean of 5 plus 4 times L1. Because this is now looking exactly like that statement, the mean of A plus BX. All right, so we ask ourselves, does the mean change by the multiplier? The answer is yes. Does the mean change by the addifier? The answer is yes. So what I'm going to do here is I'm going to take 4, I would say, oh, the mean changes by the multiplier. I take 4 times the mean of L1, and it changes by the addifier, and I would add 5, and I'd say, okay, the mean is 3. 3 times 4 is 12, plus 5, my new mean is going to be 17. Now, if I just switch the order in which I do this, and I say, oh, this is going to be 5 plus 4 times the mean of L1. Same thing. 3 times 4 is 12 plus 5 is 17. Okay, and that's exactly what this is saying. This is saying you add the constant and then you multiply by the coefficient. So the mean changes by the multiplier, the mean changes by the addifier. All you need to do is think, does this change by the multiplier? Does this change by the addifier? Yes, do it. We've done it before. Okay, coming back after the break.